Okay.
All right, well, welcome everyone. All right, good night, everyone. Thank you for coming out. Good crowd. All right, well, welcome everyone. Yeah. Oh, let's not have that. Someone on the live stream. All right, good night, everyone. Thank you for coming out. All right, let's try that again. Great. Yes, thanks for coming out. My name is Brian Jackson. I'm a professor here in the physics department. You are attending First Friday Astronomy. Welcome. Hopefully that's not a surprise to anybody. First Friday Astronomy is a monthly astronomy lecture series on the first Friday of every month. Makes it easy to remember. So if it's the first Friday of the month, 7:30 p.m. Mountain Time, we'll be having this lecture. We're in this room for this semester. As you can see, it's starting to get a little full. So we're going to move to another room later this semester. For the summer, we'll be in a different room. So if you're feeling a little crowded, don't worry. It won't be this way for too much longer. These events are publicly supported. So these are not paid for by the state, by the university, the college. You know what? You all pay for these. And so if you like this kind of programming, monthly astronomy lectures, consider donating to support this program. You can visit this URL, boi.st/astrogive, or use this QR code on your phone. That'll get you to the donation page, and you can make a donation to support this program. These programs, as I say, take place live every month. You can, of course, join us on campus, but if you prefer, you can join online. We have a live stream that you can visit at boi.st/astrobroncoslive, or you can scan this QR code. We have partnered with the Julius Jecker Planetarium, which has planetarium shows every month as well. Benjamin, do you want to just stand up and shout? We're back to the left. February 15th, no big deal. It's kids show 16 to 7:15. Until 7:30 to 8:30. When the team takes the planetarium Apple High School out on the walking dog. If you Google search Julius Jecker Planetarium, you'll know yeah, great. Thanks, Benjamin. And so, as I said, our programming here at First Friday is donation supported. We're in the process right now of raising funds to refurbish our on-campus observatory. Many of you have visited that before, but it's showing its age. That observatory on top of this building was put up there in the 1970s, so it's more than 50 years old at this point. We really want to update it and make it more accessible to the public. We'd like to set it up so that the telescope can live stream the view, that the observatory dome is all automated. If you want to find out more information about that campaign, there are flyers out on the table describing it. Again, that's a donation-supported effort, so we would appreciate any support you can give us for that. All right, with that, let me turn to our speaker. I'm very excited tonight to be able to welcome Dr. Elisabeth Adams. Dr. Adams got her bachelor's degree from Caltech, followed by a PhD from MIT. She was a postdoctoral research fellow with the Kepler mission for a while before joining the Planetary Science Institute, and is currently a senior research scientist with Planetary Science Institute. She has a really interesting variety of research. You'll hear about some of her work tonight. But one of the things that a lot of people don't know about Dr. Elisabeth Adams is she is a professional published sci-fi author and has a book. Your book is on Amazon. It's not on anymore.
Short story.
Short story. Fair enough. Okay, short story. Elisabeth has some really great sci-fi as well. So you'll hear a little bit about her sci tonight, but afterwards you can go and read her sci-fi. And with that, let's welcome Dr. Elisabeth Adams.
Can you make sure this is actually on? Hello, can you hear me? Is this on?
you might want to put it a little farther up. Just jab it as close to your mouth as you can get it. Exactly.
Try this. How about this? Can you hear this now? Everybody? No, not really? Okay. Both of our yours.
I think I'm sorry.
Wait, okay. No, there's nowhere.
You can also hold it.
All right, how about this? Does that work? Great. I'll just hold it. All right. So we are talking about finding the next doomed worlds. I know I've got some questions about what a doomed world actually is. So I will start with my first slide, which is the question people have been asking me: is Earth a doomed world? I mean, you read the news. Earth is getting hotter and climate's getting weirder and lots of bad things seem like they're happening. Like, is the planet in trouble? Well, let's give you, as a planetary scientist, I like to give a little bit of a historical perspective on, doom and destruction. Once upon a time, the entire Earth froze over and stayed that way for millions of years. This is about 600 million years ago. This is snowball or slush ball Earth. The difference is whether it froze over completely or there was maybe a little slushy layer right around the equator that still had some liquid water. This may have happened several times. This was all before life got started in earnest. So there's only a few, Okay. Sorry, 1 second. Some technical. All right. Hopefully those of you online can now see my beautiful slides. So, all right. So once upon a time, this would have been really bad news if there had been any life on Earth, but it was all single-celled organisms in the ocean and they came through okay. Back here. How about that? All right. Earth has also had one or two mass extinction events, the most famous one being the most recent one when the dinosaurs got wiped out by a asteroid impact in a shallow sea, which was pretty bad news for them. In fact, this is not the only, I'm gonna get that zoom window out of there. Sorry, how's about we go block that bit of screen? There we go. All right. So this is, there have been 5 major max extinctions in history. This is such great Friday night conversation material. I promise it gets better. So asteroids aren't the only thing that can destroy all life on Earth, or not all life, most life on Earth. I think the record was the Permian, which destroyed about 95%. You can also have volcanic activity or large cooling or heating events that can really do a number on life. So next slide, please. There we go. All right. We're not the only person, not the only planet to experience catastrophic global problems. Once upon a time, Mars had a lot of water. It had oceans. And we know this because we have sent spacecraft and rovers to Mars, and they have found evidence of the water still there. It's actually an open question whether the water evaporated into space, which is long by what people thought, or if it just sunk deep into the Martian subsurface. But it's not there on the surface anymore. If there was life on Mars, it all died out a long time ago. I mean, the planet's still there, but it was a pretty bad day for everything that lived on Mars, if there was anything. Venus also had an even worse version of this. It had a runaway greenhouse effect that caused its temperature to get so hot that the only spacecraft we've ever sent to Venus, there were some Soviet spacecraft and they touched down and they lasted for a few seconds before they melted. That's hundreds of degrees on the surface. None of those are doomed worlds because the planets are still there. Like, bad news for the life on the surface, but just because it's the end of the world colloquially as we use it, doesn't mean that the world actually ended. We're going to talk about planets where the whole planet is in trouble. So, what's enough to actually doom a planet? There's a couple scenarios I'm going to talk about next. The first one is that one you just saw right here. Something smashing into a planet could really do it. That could destroy a planet. So this is dynamical interactions are what cause planets to crash into each other. And one way of putting that is if you had a star with a single planet going around it, and there was nothing else, and that planet could happily circle that star for billions of years until the end of the universe, and nothing would happen. But as soon as you get more than one planet in a system, or you add extra stars or passing stars, then things get interesting. And they get interesting enough that occasionally giant planets collide with each other or get ejected from the solar system. In fact, for our own solar system, if you had to pick the planet that was the most likely to be doomed, it's actually Mercury. Because in the next 7 billion years, there's about a 1% chance that Mercury could get kicked out of its orbit. It's mostly Jupiter's fault. And yeah, Jupiter's the big one, tossing its weight around. And so Mercury could get kicked out, could get kicked into the sun, could get kicked into Venus, or could get kicked into Earth. This would be a very bad day for Mercury, Venus, or Earth. The sun would not care. It is, however, not very likely. It's about a 1% chance in the next 7 billion years. I don't think you should really lose too much sleep about this one. Okay, nearby supernova. That's a good one. I love this plot. I don't know how many of you are familiar with the XKCD comic, but occasionally there are ones that just nail it. So supernova are amazing and beautiful. This is the background image is the Crab Nebula, that exploded, going on 1,000 years ago, 1066. And astronomers love supernova. You can learn so much about them. We just don't want one exploding right next door. The good news for those of us on Earth is that there aren't any of the right kind of stars to explode right next door, probably. There's different kinds of supernova. And it's possible there could be a white dwarf that we haven't detected that's just close enough or could become close enough that it could explode unexpectedly. But this is unlikely. This could, however, be a problem for other planets elsewhere in the galaxy. All right, so the most deadly killer of planets, stars. I'm putting up a link to a paper there because I love the title. It's called Eating Planets for Lunch and Dinner, Signatures of Planet Consumption by Evolving Stars. So the eating planets for breakfast part is because when planets are forming, they get knocked around, and a lot of planets, baby planets, fall onto the stars and the star eats them. Gulp, delicious. But towards the end of their lives, stars also go through some processes that cause them to eat their planets too. So that's the dinner part. And lunch is, I guess, stars and planets getting unlucky. Like if Mercury got knocked around by Jupiter, that would be the sun having an unexpected planet lunch. You can see this in stars, by the way. Some of late stars, you can see pollution. You can see lots of metal in the lines of white dwarfs, and that's a sign that they just had themselves a nice planet. Okay, so we're going to talk a little bit more about stars and their taste for planets. But now we're going to move on to a little bit about our sun. Back to Earth. Actually, Earth might really be quite doomed by this. If you look at the top panel, that is where the sun is right now. And you can see how Mercury and Venus and Earth are well outside of the sun's radius. But the sun is going to expand. It is going to become a red giant, and it will expand out. It will definitely eat Mercury. It will definitely eat Venus, and it will be about the size of Earth. So the size of let me put this differently. The size of the sun will reach to approximately Earth's orbit. It's not clear if Earth will be just inside the sun or just outside the sun. So whether or not it gets eaten or just gets completely blasted is an open question that you will have to wait another 7 billion years to find the answer to. So again, maybe don't lose a lot of sleep about this, but I would say in the long term, Earth is definitely doomed by the red giant phase. That is, however, a while from now. And I have a research program and I want to do something now. So I want to find a planet that's a little more doomed, a little bit more imminently doomed. So let's move on to what we might be able to find. Okay, so this is not my research. It's just really cool. We caught a star in the act of eating a planet. Can you see it? It's very exciting, very dramatic. The kind of images only an astronomer loves. So in plot A, there is this faint, boring little star that is not very bright. And then over here, a few years later, the star has gotten a lot brighter. And it brightened very, very quickly over 10 days. 10 days for astronomers is super fast. I've been throwing around billions of years and millions of years. We like those kind of numbers. 10 days, what is that? So we are watching a star eat a planet. So the plot is just showing the brightness of the star over time. And here the star is minding its own business, nice and flat. Yeah, a little bit of jitter. This is the different colors you can mostly ignore. They're looking at different wavelengths at different telescopes. And then suddenly all of the instruments show it brightening quite a lot in the course of 10 days, and then it slowly fades back down. And this is the signature of a planet falling onto a star, and then the star dramatically absorbs all of that impact. It's a little bit like dropping a pebble into a pond, and then there's a splashback. And so there's this giant burst of energy from the star, and then it fades away and the star settles down. And, 6 months later, it's as if the planet never was. So, okay, that's really fun, but that was a star that we didn't know anything about, and it was a planet we didn't know anything about. We know that the planet was about the size of Jupiter within a factor of 100. So it could have been 10 times smaller than Jupiter or 10 times bigger. We don't really know a lot about it. Can we tell if there's a planet that we actually know something about that is doomed? Can we figure this out before it happens? And I'm not talking about our solar system, because that's a long time from now. Can we find something that's a little more doomed than a few billion years from now? All right. So I couldn't find a good picture online of the main thing I wanted to talk about. So this one's going to stand in for a little bit. This is to talk about, we're going to start talking about some giant planets, because the bigger they are, the harder they fall when it comes to doomed planets. Giant planets do not form very close to their stars. They form further out. And when the solar system is young, it has a lot of dust and gas. And so the planet can migrate inwards, interacting with the gas until it starts from a wide orbit out where we have Jupiter in our solar system. And for a variety of reasons we will not get into in this talk, it can move inwards until it finds itself on a much shorter orbit, much closer to its star, where it's much more imperiled by being right next to the star. And then the gas and dust disappears, and in theory, it stays on that nice stable orbit and is stable for billions of years. But, billions of years isn't actually forever. What happens when you get a planet the size of Jupiter really close to its sun? And this is, there's a planet Jupiter size and there's a star. It's pretty close. It's actually almost to scale on this plot. Is it has really significant tidal forces. And the tidal forces will cause the orbital period of the planet to get a little bit shorter. And then it has slightly stronger tidal forces, and the planet period gets a little bit shorter. And then eventually the planet will crash onto the star, and then boom, you see that nice spike if you're watching carefully. So the important questions here are, how close is too close, and how long is eventually? And this is what my research program that I work on with Brian Jackson is actually trying to do, is to detect these kind of planets. Okay, but this is my favorite class of planets, because that is totally to scale. You've probably seen pictures of, you've probably done the solar system walk, where you've tried to figure out how far you have to get from the sun to get to Mercury, and then to Mars, and then to, go out to Jupiter, and then Pluto's way on the far end of wherever you've set up your scale. This planet is right next to the sun. It's 3 stellar radii away. It's got to be a crazy place. It's very, very, very hot on the side of the planet that is facing the star. It's probably tidally locked, meaning that there is a very hot side of the planet, and then the backside never sees the star, which is crazy. It's good. There's crazy winds on these worlds too. Anyhow, I could talk about ultra hot Jupiters all day if you wanted me to, but I'm not going to, except to say that these are the doomedest of all planets because they're too big and they're too close. And they're very common. We don't have one in our solar system, but about 1% of G stars like ours have one. But not the older stars. The older stars don't have as many ultra hot Jupiters. Then there's some questions about why that is. I read an interesting paper that maybe the hot Jupiters are making their stars look younger, but there's another more compelling reason. This is true. This is actually true. There's another more compelling reason, that is maybe the stars are eating their ultra hot Jupiters, and that there are none left by the time the stars get to late middle age. And so that's what we are trying to figure out. So what happens to them? Well, all right. To answer this question, we are going to get into some data. And this is a planetary transit. So if you have a star and it's lined up just right with Earth, then you can see the planet cross in front of the star. And as it crosses in front of the star, it blocks a little bit of light. And if the planet is the size of Jupiter and the star is the size of Sun, that's about 1% of the light gets blocked. This is not something you can notice with your naked eye, but a telescope can pick it up just fine. The transit happens at a particular time. That's called the mid-time of the transit. And then the planet goes its merry way. And then one orbital period later, it repeats. And if you have a boring planet that's not doing anything interesting, like spiraling into its doom, then it repeats at exactly the same time. But if it doesn't have a boring orbit, if it has an interesting orbit, it looks a little bit more like this. This is what orbital decay looks like. The blue line is what you would expect if the planet had a constant period and the period were not changing. And instead, there's this extra quadratic term that causes it to look like a quadratic shape. The planet over here, the planet's transits are getting earlier and earlier and earlier and earlier as the planet is showing up a fraction of a second earlier. This is 29 milliseconds per year. So it's not a lot of time, but it works out to be a lifetime of about 3 million years. I'm going to talk a teeny bit about the data right now because this is where all the fun is. all of the challenge in actually doing this as a professional researcher. So there is data from a lot of sources shown up there. There is the black points are data that scientists have taken and published in papers. The gray points are data that people have reported to the Exoplanet Transit Database. That is amateur data. If any of you had a telescope and you wanted to go observe one of these transits and go report it, you could go Google the ETD and report your light curve, and it would show up there, and I would download your data 6 months later and add it to my add it to my list. The blue data is our own data. It's actually a pretty small telescope, which is why we have big error bars, but professionals can use small telescopes too. And then the green stuff is space-based data. This is data from the TESS satellite. We'll talk a little bit more about that later. And so it's actually kind of challenging to stitch together data from 2008 to 2023 and make these plots. I'm including this one because I really wanted to talk a little bit about the timing systems. So this is another XKCD comic, which is, event number 1 happened at time T1. Okay. And then event 2 happened at time T2. So how would you calculate how much time elapsed between T1 and T2? And the normal person says T2 minus T1. And anyone who has ever worked on timing systems said, is it impossible to know, what a sin to ask? Because, oh my God, it gets complicated. The biggest problem with timing systems is that the Earth moves and the sun moves. So if you were looking at a star that is all the way over there and the Earth is located on the close side between the sun and the star, that is a 16 minutes difference between if the Earth has moved all the way to the back of its orbit and is over here. And it takes extra 16 minutes. So if you are not careful with your times, you can add your own extra wobbles into your data just by not doing careful bookkeeping. And you have to do the bookkeeping right. And everybody who has published transits before you has to do it right and keep the times right. And it's amazing how many times the professionals mess up, including myself. Anyhow, let's move on to some data. That's probably the most technical I'm going to get with these slides. So we're going to go to some observations of potentially doomed worlds. I have a big sample of planets and I want to see which ones we might find that are doomed. All right. So the first thing we have to do is get lots and lots and lots of data. This is a 40-inch telescope in South Africa. And we have gotten over 50 light curves there in the last couple of years. One of my collaborators lives in South Africa. I apologize. I don't have the slide up that I meant to have, which shows you what an international collaboration we have. And we also have a automated telescope in Arizona. I like to point this one out because its roof is a garage door opener run thing. It's in this great shed and it's got a Do you see this line here? That's the ding where the roof ran into the telescope because it didn't close properly. The telescope's fine. This is just a baffle. The actual important stuff is back here. This is just to keep stray light from getting in. But you know, high quality scientific instrumentation. And this telescope actually was built to observe Io, one of Jupiter's moons. And so when Jupiter's up, it looks at Io. When Jupiter's down, it looks at either comets or my transiting planets is the plan. All right. And Idaho also has some good telescopes. We have a telescope out in Chalice. It's another 16-inch. And then there's the Barbie scope, a nice hot pig mount up on the roof somewhere around here that we just got online, is also working on taking transits, and there's plans for more telescopes. So there are plenty of opportunities for you guys with your nice dark skies out here to take some good data to join our doomed planet search. All right. And then finally, we're going to come to a trio of space telescopes that have been tirelessly observing data continuously since 2006, which is kind of amazing. So the first one is the one on the bottom, which is the CRO mission. That was a European mission. That was the first space-based one. And then Kepler, many of you have heard of Kepler before, which the main mission was 4 years from 2009 to 2013. And then the K2 mission, which was their attempt to still keep looking at planets even after half the reaction wheels had failed. And then, which was phenomenally successful too. And then TESS, which launched in 2018, which is, wow, 6 years ago now. And so we've got all those telescopes. Let's go look at our planets and see who looks like a doomed world. All right. So this is my data. This is from a paper that I'm going to hit submit on next Monday as soon as I'm done visiting you fine people. And the first one we can see is you don't have to pay attention to like what this plot is. Just know that the bigger the bar, the better the signal. And this blue one off at right is WASP-12b. WASP-12b is the one that I showed you earlier. That is the planet that we've been looking at. That is the best case planet that we have that people have known for a while is undergoing orbital decay. There's some other models to explain it, but orbital decay seems like the most likely one. And then there's a couple other ones. I do want to point out, though, that the ones that are shaded red are not actually having decreasing periods. They're having increasing periods. Those could be due to interactions with other planets or stars in their solar system. So they're interesting. They're just not doomed to interesting. These black ones here are up here for shame because those are planets that have mistakes, multiple mistakes in literature, and they're not actually doomed. All right. So, that is one planet out of 43. This plot is just a zoomed in version because that WASP-12b is just really so much stronger signal than all the rest of them. The rest of these ones are either increasing period orbit or they are decaying too fast to be, the planet is decreasing too fast to be orbital decay, or they are not significant. And it's kind of interesting that there are not very many doomed planets. I will bring up one more, though. This is Kepler 1658b. Kepler 1658b was actually the very first candidate that the Kepler mission found. And they didn't think it was a planet for years because it looked like they thought they had the wrong size for the planet. They thought they were looking at a Neptune-sized planet around a smaller star. And it turns out they were looking at a Jupiter-sized planet around a star that had started to evolve. And once they figured out the right size of the planet, then they got the parameters for the system right. And then they went back and looked at the timing of the planet, and they noticed that the recent transits, the ones taken with TESS, are starting to come earlier and earlier. And this one is decaying very quickly also. It is decaying, in fact, even faster than WASP-12b. But so we looked at 43 systems. Of those systems, almost half of them could have detected WASP-12b-like decay. So if all of these planets were as doomed as our favorite doomed planets, then we would have detected it in at least one or two of these, particularly these top four, WASP-19, WASP-43, WASP-18, and TRACE-3. They would have been by far the super, super obvious signals So it's interesting that we did not detect it. So maybe these ultra hot Jupiters aren't quite as doomed as we would think. Maybe they're going to hang on for a bit longer. They're probably still doomed. It's probably just going to take a little longer to find out how long it's going to take. All right. So I have one more set of slides prepared. I think I'm going through my time very fast here, and that just leaves us with a lot more time for comments later. So this is talking about, what happens after your star goes explodey. So here we go. All right. This is the life cycle of a star. So the main sequence is where stars spend most of their time over here. And then your fate kind of splits. We are on a nice average star. It's a relatively small star. So we are going to go to the red giant star phase. That's where Mercury and Venus get eaten, and maybe Earth. And then it'll turn into a planetary nebula, and then the central part will condense into this nice hot white dwarf, which will sit there for a very, 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 very long time until eventually, I guess, it fades into a black dwarf. I'm not even sure what that is. And then if we had a slightly larger star, of course, it would turn into a red supergiant, it turns into a supernova, and then either a black hole or neutron star, depending on how fast it is. None of those are great for being around if you are a planet. Except, I will say, I didn't put a slide in for this because I didn't think of it at the time. Neutron stars, there's a special kind of neutron stars called pulsars, and the very first exoplanets ever discovered were around pulsars. And we found them due to the very precise timing. So that's interesting. But now we've also started to find planets around white dwarfs, like planets in close orbits, not just planets in faraway orbits. So white dwarfs have planets too. So the interesting question is, are these planets that survived somehow, that managed to escape their fate? Or are they planets that have formed afterwards, newly reformed from the rubble of the previously doomed planets, and then have made new planets? And that is an open question that we do not know. But I think my last slide is got some data where we actually show a couple of these planets. The central thing is the star, the white dwarf, and then there's a big planets off to the side. So there are planets even around stars that have passed off the main sequence. So doomed planets, they're definitely out there. It's interesting how it seems like planets can survive things that we wouldn't have thought they could. I think there are a lot of really exciting opportunities to look for more worlds being destroyed in the future. And if you have any questions, I'd love to take them. Thank you. Yes.
So age of the stars and surrounding planets, would have worked out the dance yet?
Yeah, that's the excellent question. So the question is, shouldn't we look for planets, looking for doomed planets around newer stars? And yes, we would absolutely love to do that. It's hard to find planets around young stars, partly because it can be hard to tell which stars are actually very young. And for a variety of reasons, we just don't know very many planets around young stars. But when we find them, we definitely study them closely. Yes. Go ahead. This is a Brian question.
You decide to put a telescope in Challis, Idaho. It's very dark there. That's primarily the reason. I think there was available lands. There was a deal worked out with the county to place the telescope there. So lots of reasons. Yeah.
Right. Yes. Ooh, yes. This is a great question. Okay, so if you get two solar systems that get really close to each other, can that knock planets off? The answer is yes, absolutely. If you had a star that passed close enough to another star, you could swap planets. So this planets could just end up in the wrong solar system afterwards. The planet could get knocked on a crazy orbit, so it would either collide with one or the other stars or another planet, or it could get kicked out and go free floating in space. This is actually the least doomed option for the planet, because if it's free floating, then there's nothing for it to run into, no star to eat it. It just gets very cold and lonely. Yes. Yes, another good question. Does a star eating a planet affect its composition or lifespan? The answer is yes. This is actually one of the reasons we have long thought that white dwarfs might have planets, although it took forever to find them, is because many white dwarfs, when you look at them, they are what's called polluted, meaning they have too many heavy metals in the atmosphere that should have settled down. And they're different white dwarfs have different levels of, how many different kinds of chemicals you can detect. So yes, but ultimately it changes the star cosmetically. The star itself is pretty much unaffected because stars are so much bigger than planets. All right. Yes. Um, Yeah. So the question is, how far away are the planets? And the answer is they are a wide range of distances. We have detected a planet around Proxima Centauri, which is the closest star to Earth. And we have detected planets around stars that are thousands of light years away. And for the doomed ones they're also a range, and I don't know their distances off the top of my head. The test planets, they're probably, a few hundred light years away, and it doesn't for a transit signal, it doesn't really matter how far away it is. The main effect that has is how bright the star is, because the fainter the star is, the harder it is to search. So once they're on the other side of the galaxy, it's hard for us to look for them. But all right, there's a question way in the back. Correct. Yes. The question is, when you look at the spectral lines of a star after it has eaten a planet, can you see more heavy metals? And the answer is yes. I mean, depending on the type of star, it can be easier or harder to find the amount of heavy metals you're looking at, which is why white dwarfs turn out to be relatively easy to find, but pollution in. But yes, you can. The other question in the back. All right. So if Earth got swapped into a solar system, or yeah. So if Earth were swapped into another system around a white dwarf, in theory, in principle, if it was at the right distance from the white dwarf, it would be just fine. Yeah. Yes. Yeah. 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 Okay. Okay. So you're talking about me saying that there was a planet that its orbital period was decreasing too fast for it to be doomed. So what's happening with that system, I think, the reason I say it's too fast is because you can calculate this parameter about stars called Q. And that is just basically the measurement of how fast things in orbit will decay. And the Q that we calculate for the star doesn't make sense. It's much too small. So our alternative theory for what is happening to this planet is that it is not actually having a decreasing period, it's having a oscillating period. So it is going down and it will start going back up again, and then it will go down again. And that is caused by having another planet or another star in the solar system that is tugging on it. But we've only seen part of it and we haven't seen the rest. Yes, follow up. Yes. Excellent, excellent follow-up. Is this something we will see? Maybe. You're pretty young. So report back to me in 50 years. Yes. You, yes. And then I'll get you. Yeah. Yeah. That is a great question. The question was about the system where the star brightened and then faded back down, and whether we had gotten spectra before and after. That is, I suspect that they did get spectra. So they've definitely gotten spectra after. I don't know how it compares. I'm not sure. I would have to go reread the paper. But perhaps. Okay. Oh, yes, let's take some online questions. Sorry. Ah, very good. Hi, Melinda.
Melinda online asks, what future data sets are you looking forward to most when it comes to the topic of doomed planets?
Ah, yes. Well, future data sets. I mean, I would love to see 100 more planets falling onto their star like that first one. We would really like to see some more. There's what's the telescope I'm thinking of? The Roman telescope is going to launch in the next couple of years, and we'll be looking at a whole bunch of stars in these near the galactic center. But also, I'm really excited at just getting to keep looking at some of these planets a little bit longer. The first planet we looked at, WASP-12, showed its orbital decay in about 10 years. A bunch of these other ones are just decaying more slowly, but it's been, almost 20 years for some of them, 10 or 15 years from now. Like, that might be enough time that we will start to see them decaying, and then maybe we'll get a good sample, because they should mostly be doomed.
Rachel asks, have astronomers observed any solar systems crossing through each other? Like the way you
Solar systems crossing through each other. Ooh, that is a good question. I do not know if we have observed any solar systems crossing through each other. We have, you can run simulations backwards for Earth and figure out if we have gotten near other stars and when we will get near other stars in the future. And that's actually kind of a fascinating experiment to do, because there are some stars that will pass pretty close to the Earth in, very short astronomical time scales of, few 100 million years and could perturb other planets. Those are the kind of things that could also knock off a Mercury or a Pluto or something from our solar system. But we have not, to the best of my knowledge, seen a merger. I would love to see one of those.
And let me get the last one.
One more online.
Yeah, this is the last one. What new planetary discoveries has the Webb telescope unearthed?
I mean, lots. Oh man, that's a whole other talk. Let me think about a good one. I don't have one off the top of my head. I'll come back to you on that one. Take another one from the room. All right. Red sweatshirt. Oh, okay. So this is if the star is on a path to be a black hole or a neutron star. Which one does it take? It all depends on how big it is. To become a black hole, you have to have a particular mass. I want to say 8 times the mass of the sun-ish. And so if you are not heavier than that, you will become a neutron star. But if you are heavier than that, you can't avoid becoming a black hole. Like, that's just your fate if you are a star. Yes. Yes, you. All right. Yep. Okay. So the question is, what's a WASP? Yeah, this is how astronomers name planets. So WASP stands for, I think, the Wide Angle Survey for Photometry. It is a network of telescopes that discovers planets. So WASP-12 was the 12th planet that the WASP survey found. Yeah. Yeah. What a great question. I don't know that one off the top of my head. Sure, possibly. I'm sorry, I just don't remember. Yeah. Yeah. Yeah, yeah. No, I can look it up for you. It's just not on the top of my head. This is all right. The ones here, I will defer you to Brian. What kind of cameras you have on your telescopes here, or perhaps to
Do you
Rachel.
happen to recall, Rachel? What camera we have on the scope upstairs?
Right. Right. You can get your color if you want colors. You can get your colors the old-fashioned way by using different filters and combining them. All right. Question. If two solar systems collide, could they stabilize a doomed planet's orbit? That would be so it would be tricky because these doomed planets are very, very, very close to their stars. And those are the ones that are the hardest for a passing star to perturb. So, like, the planet is right on top of its star. The planets, if you have two solar systems passing through, it's the planets that are a little further away that are most likely to get impacted. That said, there could be some kind of just so scenario where some other planet got knocked in and interacted with the hot Jupiter, and the hot Jupiter moved further out and was suddenly not doomed anymore. But I would not say that was a very likely scenario. Yes. Yeah. They're Jupiter. Think Jupiter. So this. Oh, okay. Yeah. So these stars are about 1,000 times more massive than Jupiter. So they don't make a big dent. No. The whole solar system could crash into the sun, and except for the angular momentum problem, like the sun would just be fine and would not really notice. Yes. Yeah, about a day or two is the typical orbital period. WASP 12b, oh, I'm sorry, I didn't have that up there, has a 1.09 day period. The shortest period we know about for a Jupiter-sized planet is 19 hours, which is about 0.6 or 0.7 days, 0.7 days. The shortest period we know about any planet around a star is 4 hours, which is practically on the surface of the star. That is for something that is about Earth size or a little bit smaller than the Earth. You can guarantee that that planet has absolutely no atmosphere left and is blazingly hot. But strangely enough, the tidal forces are not strong enough to move that thing into the star over billions of years. It's because it really depends on the mass of the planet. So you could park Earth right next to the sun, and it would be bad news for life, but the planet would not be doomed if it was sitting closer than WASP 12b is. It would just sit there happily baking for the rest of eternity until the red giant phase, I guess. Yes. Okay, great. Good question. So I mentioned that there were crazy winds on these planets, and the question is, how do you know that? And the answer is, well, obviously we do not have weather stations on these planets, but you can do some modeling and some very simple calculations. And the most basic calculation you do is it is blazingly hot on the one side, and it is much, much colder on the back. So the heat wants to move, and it wants to move very quickly. And so you can get in some cases, I think, supersonic winds and just like tearing around. And you can actually see on some planets, you can see the offset in the brightness of the brightest point of the planet that we think is due to the winds pushing it off course. So this is actually something we have measured with data. It's cool. One more
Question?
question. And yes, how about you in the white hat? That is such a good question. And I wish I knew. Like, we suspect we probably did not have a hot Jupiter-sized planet. And the reason we suspect this is because we have Mercury, Venus, Earth, and Mars are still around. If we had had something the size of Jupiter that had moved in, it would probably have knocked all of the inner planets out, and they would have, been eaten by other planets or kicked into outer space. But it's a great question. It's not inconceivable that there could have been a very early gas giant that got eaten in 4 billion years ago. We just don't know. All right.
Great. Let's thank the speaker again.
Yeah. Thanks, everybody. This has been fun.
And join us again next month where we're going to hear about spiders on Mars.
I love it too. How did she know?